Welcome back to the Deep Dive. We're here to really get you from zero to deeply informed on key topics. And today we are digging into infrastructure as code IaC. Specifically, we're focusing on, well, the big one, HashiCorp Terraform.
Yeah, our goal is pretty clear. We want to break down the core ideas you need to get Terraform. We're talking providers, resources, state, modules, the whole lot. By the end, you should really understand why IaC isn't just, a nice to have. It's basically mandatory now for handling modern cloud infrastructure. Terraform, fundamentally, it automates away so many headaches. It brings consistency where, honestly, doing things manually is just asking for trouble.
Right. And crucially, this isn't just theory today. The source material we're synthesizing, it's not just slides. It's a full crash course. It blends the core concepts with actual demos, and it all builds up to deploying a real application. We'll see through the synthesis how a Node.js app gets deployed onto AWS, start to finish, all managed by code. So yeah, let's dive into the blueprint for automation. Okay, first things first, let's set the stage. Infrastructure. It used to mean like big server rooms, right? Cold, noisy places. But in today's cloud world, what does infrastructure really cover?
It's basically everything that your application needs to run. Think of the app as the car's engine. The infrastructure is everything else. The chassis, the network cables, the power. So servers, obviously, whether they're VMs or containers. Then there's all the networking stuff, load balancers, IP addresses, DNS, all those routing rules, and crucially, the firewalls, your security groups, plus databases, of course, and any monitoring systems you need to, make sure it's all actually working.
And managing all that for a long time was very physical, very manual, that whole traditional on-premise way of doing things.
Exactly. It was all done by hand inside physical data centers. Picture those huge rooms, rows and rows of servers. If you needed a change, like say patching the OS or updating a database schema, a user would file a ticket, then you'd have dedicated sysadmins who had to physically or, remotely log into specific machines, apply the fix, test it out, and then close the ticket. This whole back and forth, it got known as the ticket loop.
Wow, that sounds incredibly slow and frankly prone to errors, right?
Oh, absolutely. It kind of worked okay when apps were simpler and changes didn't happen very often. But the moment things started booming, the digital revolution kicked off. Well, that manual approach just completely fell apart. We went from managing maybe dozens of servers to hundreds, then thousands. It just became a massive scalability crisis. Manual processes couldn't keep up. Every little change meant fiddling with config files on potentially hundreds of machines, all interconnected. It meant very little flexibility and just constant firefighting when things broke.
I can just picture the stress, getting paged at 3 a.m. because, one config file on server 47 was slightly off compared to server 48 and the whole thing falls over.
That's exactly the kind of thing that happened. And the money side was just as bad. Let's say you bought 50 physical servers for the holiday rush. Then maybe the market shifts, demand drops. Suddenly you've got these 50 expensive boxes just sitting there, burning power, still needing maintenance, capital just tied up. Scaling down was a real financial headache.
Okay, so that sets the stage for the cloud, which basically shifted things to a renting model, solving those physical pain points.
Yeah, the cloud was a game changer. AWS, Azure, GCP, they took on the burden of the physical hardware, the maintenance, the basic scaling. Infrastructure stopped being things you plugged in and became, essentially, APIs you could call. I mean, even clicking buttons in the AWS console, that's just a nice UI on top of API calls, right? Like the S3 API reference shows. This gave us amazing scalability, spin up thousands of instances in minutes, and cost efficiency. Pay for what you use.
But, and this is the crucial part, the cloud didn't solve all the problems. It actually introduced a new, maybe more subtle one, configuration drift.
That is the core insight, yes. The cloud UI, it made things easier than the old ticket route, sure. But you still had to manually click through to configure everything. You set up your EC2 instance, tweak the security groups, define network settings, configure the RDS database, click, click, click. Now imagine you've got a setup with, say, 20 different resources, and you need it replicated in 3 different regions for reliability, US East 1, US West 2, maybe AP South 1. You have to do those 20 manual steps 3 separate times.
And every click is an opportunity for human error. Multiply that out.
It's basically guaranteed you'll get inconsistencies. That manual repetition leads straight to what we call configuration drift. What it means is your environments aren't identical anymore. They're not reliable mirrors. For example, maybe in US East 1, your MySQL database is running version 8.3, fully patched, secure. But the admin deploying to US West 2 was rushed, maybe missed a step, and that one's still on 8.1. Now, if you've got hundreds of people managing thousands of components, that small difference, it could hide huge security holes or cause really weird application bugs that are impossible to track down.
So the need becomes crystal clear. Enforce consistency. Eliminate the manual clicking. Which brings us squarely to the solution. Infrastructure as code, right? So that nightmare of manual management, the drift problem, that's exactly why IaC exists. Let's nail down the definition. What is IaC formally?
Yeah, infrastructure as code, or IaC. It's the practice of managing and provisioning all your compute infrastructure. It could be cloud, could be on-prem stuff too, like VMware using machine-readable configuration files. Basically, instead of clicking buttons or running manual scripts, you write code that describes your infrastructure.
And the fundamental idea, the philosophy behind it, is managing this desired state, right?
Absolutely. That's the core contract. You, the user, define the desired state in your code. You say, I want a server this big on this network with these firewall rules running database version 8.3. Then the IaC tool like Terraform does the heavy lifting. It looks at your desired state, compares it to the current state, what's actually out there right now, and figures out the exact steps needed to make reality match your code.
So if I change just one line in my code, say, I want a bigger server size, Terraform doesn't just tear everything down and start over.
Exactly. That's the power of its declarative nature. You told it what you wanted, a bigger server. Terraform calculates the how. And usually, for something like a size change, it can often just update that specific parameter without destroying the whole resource. It's much smarter than a simple script.
Okay, this immediately tackles those problems we just outlined. What are the big concrete wins you get from using IaC?
The benefits map directly onto the pain points of doing it manually. First, consistency. This is huge. If you write the configuration once, in code, and then you deploy that same code to your dev environment, your staging, your production, maybe across multiple regions, they will be identical. That whole MySQL 8.3 versus 8.1 problem, it just disappears because the code mandates 8.3 everywhere. Configuration drift is effectively eliminated.
Second benefit has to be automation, reclaiming all that time spent clicking.
Yes, absolutely. You automate the entire life cycle, creating resources, changing them, hooking up monitoring, eventually tearing them down. It's all automated. Once you've written the code blueprint, deploying becomes like a single command. It saves engineers tons of time and effort, letting them focus on, more important problems than just clicking around in a UI.
And the third big one you mentioned is borrowed from software development, version control.
This is so critical, especially for teams and for security, because these config files are code. They belong in Git or GitHub or whatever version control system you use. Every single change is tracked. Who changed what, when, why. It can be reviewed through pull requests, just like application code. This lets teams collaborate effectively. And crucially, it allows for reuse. Imagine Team 2 needs the exact same setup as Team 1, just in a different region. They don't start from scratch. They clone Team 1's repo, change maybe one variable, the region variable, and run Terraform apply. Setting up complex infrastructure becomes reliable, repeatable, and auditable.
Okay, so IaC is the concept. Terraform is arguably the most popular tool for implementing it. Why Terraform? Why has it become such a standard, maybe over native tools like AWS CloudFormation?
I think the biggest reason is its cloud agnosticism. CloudFormation is great, but it only works for AWS resources. Terraform, though, it can manage resources across AWS, GCP, Azure, even other things like Kubernetes or Docker, all using the same basic workflow in the same language. It gives you a single pane of glass,
Then what is that language, HCL, right? Why invent a whole new language for this?
Yep, it's the HashiCorp configuration language, HCL. It was designed specifically to be easy for humans to read, but also easy for machines to parse, and really focused on defining configuration. Now, why a new language? Well, think about using generic formats like JSON or YAML for complex config.
Oh yeah, deeply nested JSON. Trying to read or debug that can be a real pain.
Exactly. HCL has some big advantages. It natively supports comments, for one, which is tricky in strict JSON. It has much more powerful ways to do string interpolation embedding dynamic values. And it supports more complex logic, like conditional expressions and functions right in the config. That focus on readability and config-specific features makes HCL, frankly, much better suited for describing infrastructure blueprints than trying to force everything into JSON or YAML.
Makes sense. A purpose-built tool for the job. You also mentioned its approach is declarative. This feels like a really core concept to grasp.
It is absolutely fundamental. The opposite is imperative. Imperative tools need you to write scripts saying how to get to the end state. Step 1, create the network. Step 2, wait 5 seconds. Step 3, create the server. Step 4, attach the server to the network. You get the idea. Terraform, being declarative, you just tell what you want the end result to look like. Terraform itself figures out the dependencies, the correct order of operations, all the underlying logic. It takes a huge burden off the engineer.
Okay, but if Terraform is cloud agnostic, how does this one tool know how to speak the unique, complex API language of AWS and Azure and GCP and so on?
Ah, that's where the magic of providers comes in. Terraform itself doesn't talk directly to the AWS API or the Azure API. It uses a middle layer, a plugin called a provider. Think of the provider as the official translator for each specific platform. The AWS provider knows how to talk to AWS APIs. The Azure provider knows Azure APIs, etc. It abstracts away all those complexities and differences. This lets your HCL code look remarkably similar, whether you're defining an AWS EC2 instance or a Google Compute Engine instance. The provider handles the dialect conversion, if you will.
Got it. The provider handles the translation.
Yeah.
Okay, let's walk through the standard workflow, the 3 stages every engineer uses every single time.
Right. The workflow is built for safety and predictability. It's always these 3 steps. 1, right. This is where you actually author your infrastructure definition using HCL in your .tf files. This is you defining that desired state. 2, plan. Terraform plan. This is absolutely critical. It's your dry run, your confirmation step. Terraform reads your code desired state, compares it against what it knows exists, current state, via the state file, and generates an execution plan. It tells you exactly what it's going to do. I plan to add 3 resources, change 1, and destroy 0. Importantly, no changes are actually made to your infrastructure yet. 3, apply. Terraform apply. Once you've reviewed the plan and confirmed it looks correct, you run apply. Terraform then executes those steps, making the actual calls to the cloud provider to create, update, or delete resources until reality matches your desired state.
That plan step, showing you the exact impact before you commit. That seems like the ultimate defense against those accidental middle-of-the-night manual mistakes, doesn't it? All right, let's get into the nuts and bolts. We've picked our provider, say AWS. We've run Terraform in it to download that provider plugin. Now we need to actually define the stuff we want to build, the serverless sources. How does that look in the code?
Resources are the basic building blocks, yeah. The syntax is pretty straightforward. Resource type local name. The type tells Terraform what kind of thing you want. For AWS, that might be OS instance for an EC2 virtual machine, or OSBinstance for an RDS database. Now, the local name, this part is really important to understand. This name is purely for Terraform's internal use. It's how you refer to this specific resource within your Terraform code, maybe to link resources together or use its attributes in variables. It is not necessarily the name that resource will actually have when you look in the AWS console. That's usually set by a separate argument inside the resource block, like a name tag or something similar.
Okay, so plan and apply, handle creating and updating. What about getting rid of things? The end of the life cycle.
That's the Terraform destroy command. It's basically the reverse of apply. It looks at the state file and figures out how to remove everything that Terraform is currently managing in that configuration.
Okay.
And just a quick safety note here related to what you mentioned earlier. You can technically run Terraform apply auto-approve to skip that manual yes confirmation. But the sources we looked at and general best practice strongly advise against doing that, especially in production. The risk of accidentally confirming a plan that destroys critical, expensive infrastructure is just way too high without that final manual check.
Yeah, that destructive power.
Sure.
It really highlights the importance of the next piece,
Yeah.
the state file. If one command can potentially wipe everything, Terraform needs an absolutely reliable record of what it's managing. Why is this state file so fundamental?
The state file is essentially Terraform's brain, its memory. It's usually a file called terraform.tfstate, and it's basically an internal database, typically stored in JSON format. It keeps track of every single resource that Terraform has provisioned and currently manages. This is the definitive current state. You can think of it like a master inventory list or a receipt. When you run Terraform plan or apply, Terraform doesn't need to scan your entire cloud account. It just compares your HCL code, the desired state, against this state file, the current state, to see what needs to change. Without that state file, Terraform has amnesia. If you lose it, Terraform might think all your existing infrastructure is new and try to create it again. Or worse, it loses track of resources it was supposed to manage, leaving them orphaned.
Whoa. Okay, that sounds like a single point of failure potentially. What happens if the actual infrastructure in the cloud gets out of sync with this state file? That's state drift, right?
Yeah, state drift is a major headache for IaC users. It happens when someone makes changes to the infrastructure outside of Terraform. Maybe an engineer logs directly into the AWS console and manually changes an EC2 instance size, or worse, deletes a database that Terraform thought it was managing. Now, Terraform's state file still thinks the old configuration exists because nothing told it about the manual change. The map no longer matches the territory.
So how do you fix that mismatch? What's the process?
There are really two ways to approach it, and it's important to understand the difference in philosophy. One, the recommended way. Run Terraform plan. Terraform reads your HCL desired state, checks the state file, recorded current state, and then actually queries the cloud provider, real current state. It sees the discrepancy. Hey, the code and state say this database should exist, but AWS says it's gone. It identifies the drift and proposes a plan to fix it, usually by recreating the missing resource or reverting the manual change. This upholds the IaC principle. The code is the source of truth, and reality should match the code. Two, the generally discouraged way. Terraform refresh. This command does the opposite. It queries the cloud provider to see what really exists, and then updates the state file to match that reality, completely ignoring your HCL code's desired state. So if that database was manually deleted, refresh would just remove it from the state file. We generally discourage this because you're basically saying reality dictates the state, not your code. It leads to confusion later because your code defines something that Terraform no longer knows about in its state.
Right, the lesson seems to be always trust the code as the source of truth and use Terraform to enforce it. Okay, let's talk security. Where does the state file live? The default sounds risky.
It's incredibly risky by default. Out of the box, Terraform stores the terraform.tf state file right there on your local machine, in the same directory as your code. Now, even if you mark certain variables like passwords as sensitive in your HCL, the state file itself often contains a lot of detailed configuration info, potentially including things like database endpoints, private keys, or other sensitive credentials, all in plain text JSON. If someone accidentally commits that local TF state file to a public Git repository, well, that's a massive security breach waiting to happen.
Okay, so nobody does that in a serious setup. The standard practice is using a remote backend then.
Absolutely. For any team or any production workload, using a remote backend is pretty much non-negotiable. Things like storing the state in an AWS S3 bucket or Azure Blob Storage, or using HashiCorp's own Terraform cloud. Remote backends give you three huge advantages over local state. First, security. The sensitive state file is stored centrally in a secure, managed location, not scattered across engineers' laptops, and definitely not in Git. Access can be tightly controlled. Second, versioning. Many remote backends automatically version your state file every time a successful apply finishes. It's like Git commits for your infrastructure state. If a deployment goes wrong, you can often roll back the state to a previous known good version, which is incredibly useful for recovery. Third, and maybe most importantly for teams, locking. What happens if two engineers try to run Terraform apply on the same infrastructure at the same time? They could override each other's changes or corrupt the state file. Remote backends provide state locking, ensuring that only one operation can modify the state at any given moment. It prevents race conditions and keeps things orderly.
Okay, we've covered defining resources and managing their state, which is critical. Now let's talk optimization, making our IaC code cleaner, more reusable, more dynamic. This brings us to variables and modules. Let's start with variables. How do they help us avoid hard coding everything?
Variables are absolutely essential for making your Terraform code reusable and flexible. Instead of writing region UCS1 directly in your resource block, you define a variable for the region. This means you can use the same code template to deploy to different regions or environments just by changing the variable values you pass in. We generally break them down into three types. One, input variables. These are the main way you parameterize your configuration. You declare them, often in a variables.tf file, to accept values from outside the configuration, things like the environment name, dev, staging, prod, the AWS region, maybe the number of servers you want. They make your code adaptable. You can give them default values too. Two, local variables, or locals. These are different. They're defined and used only within a specific module or configuration file. They're super useful for defining complex expressions or values that you need to reuse multiple times within that file, but don't need to expose to the outside. For example, maybe you construct a resource naming prefix based on the environment and project name. You define that logic once as a local variable, then reuse the local variable wherever you need that prefix. It keeps your code DRY, don't repeat yourself, and much more readable. 3. Output variables. These are how your Terraform configuration communicates important information back to you after it runs. Once Terraform creates, say, a web server and a database, You'll want to know the server's public IP address or the database's connection endpoint, right? You define output variables to expose these values. After Terraform apply finishes, it prints these outputs to the console. It saves you having to dig around in the cloud provider's UI to find that critical info.
Right, makes sense. Now, inputs seem powerful, but what happens if you define the same input variable like the server size in multiple places? Which one actually gets used? There's a hierarchy, isn't there?
Yes, and understanding this precedence order is really important for avoiding surprises. Terraform needs a clear rule for which value wins if it's defined in several spots. The hierarchy, going from highest priority, the one that always wins, down to lowest, is generally 1. Command line -bar flag. If you explicitly pass a variable value when you run the command, like Terraform applied to Terraform instance type t3.large, that value overrides everything else. It's the most direct instruction. 2. Environment variables. Variables set in your shell environment, specifically prefixed with TFEAR, like export TFVA RDB password super secret. This is actually the recommended way to handle sensitive values like passwords or API keys because the secret value itself never gets written to your code files or checked into Git. It's passed in securely at runtime. 3.tfr files. These are separate files where you can define variable values. Terraform automatically loads terraform.tfrs if it exists, and also any files named .auto.tfrs. You can also specify other .tfr files using the -var file flag. These are great for grouping variables, maybe per environment, dev.tfrs, prod.tfrs. 4. Default value. The default value you can optionally specify right inside the variable block in your HCL code. This is the lowest priority. It only gets used if the variable isn't set anywhere else.
Okay, that clarity is crucial, especially for managing secrets via environment variables. Now let's talk about organizing larger configurations. We need modules. Why do modules become essential once you go beyond a few simple resources?
Modules are all about managing complexity and promoting reuse. Imagine trying to define everything providers, maybe 20 or 30 different resources, all the variables, outputs, all inside one giant main.tf file. It would become completely unreadable, unmaintainable, and impossible to reuse pieces of it elsewhere. A module is essentially a self-contained package of Terraform configuration. It's usually just a directory containing its own set of .tf files that define a logical group of related resources intended to be used together.
Can you give a classic example? What's a perfect candidate for being turned into a module?
A really common one is setting up a standard application server. You probably need, let's say, an EC2 instance, a security group associated with it to control network access, maybe an elastic IP address, and perhaps an IAM role giving it permissions. That's maybe 4 or 5 separate resource blocks in Terraform. Instead of copying, pasting those 5 resource definitions every time you need a new app server, you package them together into a dedicated app server model directory.
So then, instead of running those 5 resource blocks again and again, the engineer just calls the module?
Exactly. In their main configuration, they use a module block. It looks something like module my web server. Inside that block, they just need to provide a few key things. The source, telling Terraform where to find the module's code, could be a local path or a Git URL, maybe a version constraint, and then any input variables that the module requires, like what size instance do you want, what's the application name. Suddenly, creating a fully configured web server stack goes from maybe 100 lines of HCL down to maybe 10 lines calling the module. It drastically simplifies the main configuration, ensures consistency every time you deploy that stack, and really embraces that DRY principle.
And modules can come from different places, right?
Yeah.
There's the main code and then these child modules.
Correct. We talk about the root module, which is just the main directory where you're running your Terraform commands from. Any modules called by the root module are considered child modules. These child modules can be local modules, custom ones you've written yourself, living in subdirectories within your project. Or, very commonly, they can be sourced from external locations, especially the public Terraform registry. This is a huge resource. Communities and vendors publish pre-built, often complex and well-tested modules there. For instance, setting up a proper, secure, multi-availability zone VPC network on AWS involves defining VPCs, subnets, route tables, internet gateways, NAT gateways. It's really complex to get right manually. But there are excellent, widely used VPC modules on the registry. You can just use one of those, pass in maybe 5 or 10 input variables defining your specific needs, and get a best practice network set up with minimal code on your end. It saves a massive amount of time and effort.
Okay, let's tie all this together. The source material culminated in a practical project, deploying a Node.js app with a MySQL database onto AWS, all using Terraform. What were the key pieces of infrastructure that Terraform had to provision for this?
Right. The goal was a working web application. So the Terraform code needed to set up the entire stack. This involved an S3 bucket, probably for storing static files like images or CSS. An RDS instance, this was the managed MySQL database. The Terraform code even handled creating the specific database schema, Domo, needed by the application inside that RDS instance. An EC2 instance, this was the virtual server where the Node.js application code would actually run, listening on port 3000. And importantly, several security groups, these act like virtual firewalls, controlling what network traffic could reach the EC2 instance and the RDS instance. The example cleverly used the default VPC provided by AWS. This was smart because setting up a custom VPC network manually is quite complex, like we just discussed with modules, and would have distracted from the main goal of learning Terraform resource management. Using the default VPC kept the focus tight.
That sounds like a fairly standard web stack. But getting it all working automatically with Terraform requires some smart connections, some dynamic linking. What were some of the implementation details that really showed off IaC best practices?
Yeah, there were a few really neat things in how they wired it all together. I'd highlight three. First, the security group dependencies. This was crucial for security. They didn't just open up the MySQL port 3306 on the database to the whole internet or even the whole VPC. Instead, the RDS security group's ingress rule, the rule allowing incoming traffic, was configured to allow traffic on port 3306 only from the specific security group ID attached to the EC2 application server. This creates a direct, necessary dependency chain. The database only talks to the app server, nothing else.
And Terraform figures out that dependency, right? It knows it has to create the EC2 security group first, get its ID, and then create the RDS security group rule referencing that ID.
Exactly. Terraform handles that ordering automatically based on the reference in the HCL code. It understands this needs that to exist first. Second highlight was the use of user data for automation. Getting the Node.js application actually running on the EC2 instance wasn't a manual step after the instance was created. The auth instance resource block in Terraform included a user data argument. This argument contained a shell script, bash script. When the EC2 instance boots up for the very first time, AWS automatically executes this script. And that script did everything needed to set up the application. It cloned the Node.js code repository from GitHub, installed Node.js and NPM, installed the application's dependencies, and then started the Node.js server process. That's true zero-touch provisioning. The instance comes up, configures itself, and starts running the app all automatically.
Okay, that's cool. But the third highlight seems even more critical for making that automation robust. How did that user data script know how to connect to the database? You can't hard code the database address.
No, absolutely not. Because when Terraform creates an RDS instance, AWS assigns it a long, unique DNS endpoint hostname. And if you ever destroy and recreate that database, you'll get a different hostname. Hard coding wouldn't work. So the clever part was how the environment variables needed by the Node.js app, like db hostname, db user, db password, were set inside that user data bash script. They weren't hard-coded strings. They were populated using Terraform's interpolation syntax, dynamically referencing attributes of the RDS resource that Terraform had just created. For example, the database hostname might be set using something like export db hostname, als dbinstance.tfrdsinstance.endpoint. Terraform resolves that reference before it passes the script to user data. So the script that runs on the EC2 instance has the correct current database endpoint baked into it automatically. The application connects successfully first time, every time, even if the underlying database details change. That's really powerful dynamic configuration.
Wow. Okay, and finally, they demonstrated modularity by replacing one of those manually crafted security groups with one from the registry.
Yeah, that was a great way to illustrate the benefits of modules in practice. They took the fairly complex EC2 security group definition they'd written manually, with rules for SSH, HTTP, and the custom app port, and replaced it with a call to a standard security group module from the Terraform registry. By using the module, they could achieve the same result by just specifying standard required rules like HTTPS 443 TCP or SHE TCP, and then adding their custom rule for port 3000 as an input variable to the module. The end result, the security posture, was identical, but the amount of HCL code needed in their main configuration was drastically reduced. It perfectly showed how modules lead to cleaner, more concise, and more maintainable code by leveraging pre-built tested components. And yeah, the whole process wrapped up by showing useful commands like Terraform statelist to see what Terraform knows about, and Terraform state show resource to see details, and then of course running Terraform destroy to cleanly tear down everything that had just been built. #, #, outro.
Well, that really was quite a journey. We've traced the evolution from manual clicking and the resulting chaos of configuration drift, all the way to the structured, reliable world of defining infrastructure as code with Terraform. Hopefully you listening now have a solid grasp of the fundamentals, why that state file is so critical, how providers act as translators, the declarative approach, and why modules are key for scaling your designs.
Yeah, the immediate takeaway is you should now understand the basic mechanics of how Terraform works. But the bigger, longer-term thing is about thinking differently. The next step isn't just writing more code, it's about designing your infrastructure in a modular, reusable way right from the start. Thinking about how components fit together, how they can be versioned, how they can be tested. It's an architectural shift.
That focus on design, auditing, and the whole life cycle. It does bring up a final, maybe provocative thought for you, the listener, to ponder. We've talked about the power, but also the danger of Terraform destroy. One command, potentially wiping out your entire production stack. So the question is, beyond just basic IAM controls, what kind of granular security protocols or workflow safeguards should you build into your IaC process itself? Especially when you have complex modular infrastructure spanning multiple sensitive environments. How do you prevent that accidental catastrophic deletion without just locking everything down so tightly that nobody can get work done? What internal checks and balances are needed? Something to think about as you start building your own infrastructure blueprints with Terraform.